So in this video, we're going to use calculus to maximize the volume of a box. So it says a manufacturer wishes to design an open box. So this means that the lid is missing, that has a square base and a surface area of 105 square inches. What dimensions will produce a box with maximum volume? So we're trying to maximize volume under a square inch restriction on the surface area of the box. So step one, let's just draw an open box. So here's my open box. So I'm going to draw a picture of the situation that I'm modeling. So give myself a little box here. Let's see, we can't see on the inside of the box unless we're Superman. So assuming no X-ray vision, we won't be able to see that part. And then usually a box is going to be length times width times height. But we are told that the base is a square. So if the base is a square, that means length equals width. Length equals width. And a box volume, it says what dimensions will produce a box with maximum volume. We're trying to maximize volume. So an equation for volume using length, width, and height would simply be volume is equal to length times width times height. Here I have an ancillary equation or secondary equation that length equals width. So I can actually replace the length here with width. So my box volume is actually going to be width times width is width squared times height. So I can reduce a function here of 3 variables to a function of 2 variables using this relationship here that length equals width. So we get width times width is width squared times height. I still have a function of 2 variables. And because Calc 1 uses single variable calculus, I need to get this down to a function of a single variable. But I've been given some additional information. So I got my first ancillary equation from the fact that I had a square base. But now I also know something about the surface area. So the surface area, I'm told, is 105 square inches. Sorry, 150 square inches. But how do you calculate surface area? Well, that's just going to be the sum of the areas of the faces of the square box. So the other way we can calculate surface area is to recognize that we're going to get the area of the base. The lid's missing. So the area of the base of the box is just going to be width times width is width squared. That's the area of the base. Plus, if I look at these vertical faces, they're going to have width W and height H. So they're rectangles. So we just get height times width or width times height. And then I want to recognize that I have 1, 2, 3, 4 of those. So the surface area is actually going to be width squared plus 4 times width times height. So the fact that the surface area has to add up to 150 lets me get a formula: width squared plus 4 times width times height. The surface area formula has to add up to the 150 square inches. And then if I look at this equation that involves height and width, which are the last 2 variables I have over here in my volume function, I want to use this equation to rewrite my volume function as a function of 1 variable. So I look at this and I want to identify which of the 2 variables, W or H, is less complicated to solve for. And in this case, hopefully it's clear that H will be easier to solve for than W would. So I'm going to go ahead and solve for H. So I would subtract W squared from both sides. And then divide both sides by 4 times the width, which will isolate H. So there's a couple steps there. I did kind of skip some steps, so you might want to scratch that out on your own piece of paper if that was a little too fast. So H can go right here where H is in the volume function. I can replace H with this stuff here that's all in terms of the width W. So I get width squared times height, but height is the same as 150 minus W squared over 4 times the width. And I see the width will go into width squared, so we get a W. So if I simplify this, I'll get a fourth. I have a 4 in the denominator. A fourth of, distribute the W that's remaining into the parentheses. I get 150 W minus W cubed. So this is volume as a function of a single variable width, and that's what my goal was. My goal was to take and find a formula or a model for the variable I wanted to optimize, and we're trying to optimize or maximize volume. And then we need to use ancillary equations. Here's one, here's another, ancillary equations to reduce it to a function of a single variable, because in Calc 1, we only know how to deal with single variable equations. So this is the equation I'm going to try to optimize. I want to determine a feasible domain for this model, or a contextual domain for this model. So one way to do that is just to kind of think about extremes. We know that the width can't be negative because box dimensions aren't going to be negative. So we could say, well, what if we make a really stupid box and we just say, hey, the width, the smallest the width can be is 0. It'd be a dumb box. It'd be 0 by 0 by height. In fact, the volume, because volume equals length times width times height, if we let the width be 0, the volume of the box would be 0, because we'd have this kind of degenerate box. But that would be kind of a worst case scenario, would be to say, hey, let the width of my box be 0. And then to get the other end of the feasible domain, what we can do is look at the surface area model right here. We get width squared. We know that width squared plus 4 times width times height has to add up to 150. What if we had another degenerate box where we just let the height of the box be 0? And of course, if we let the height of the box be 0, we'd get 0 times width times length is 0. We would get a box with no volume because it would have no height. But that would be kind of the other extreme case, would be to say, hey, suppose the height is 0. If the height were 0, this term would go away, and we would get the width squared is equal to 150. So the width of the box would be the square root of 150. I don't need the plus or minus because width can't be negative. And 150 is really 25 times 6, which simplifies in reduced radical form to 5 times the square root of 6. So the extreme case, if we let the height be 0, the biggest the width could possibly be would be 5 times the square root of 6 inches. So there's a feasible domain for my model. The width is going to run from 0 to 5 times the square root of 6. And what we want to recognize in particular is that if the width is 0, then the volume will be 0, because we'll have 0 times length times height is 0. So volume at width of 0, volume is going to be 0. And similarly, if we plug in 5 times the square root of 6 to our function right here, we're also going to get a 0, because this was predicated, the second calculation was predicated on our letting height equal 0, and we know when the height is 0, the volume will also be 0. So here's why this is important. We're guaranteed, because I have a closed interval over which my volume function is defined, and we know at the endpoints the volume is 0. We know that's the minimum volume. You can't have negative volume, so the minimum volume is 0, which means if we find a single critical point for the function v of w on the closed interval from 0 to 5 times the square root of 6, that critical point, by the extreme value theorem, will correspond to a maximum volume. So the next step is to find the critical values of your function, because those are the places where you can get relative minima and relative maxima. And this extreme value theorem, in this case, based on our feasible domain, is going to give us a maximum volume. So remember, to find the critical numbers, we need to know the derivative. So the derivative of this function is going to be 1/4 times the derivative of 150w is just 150 minus The derivative of w cubed is 3w squared. There's my volume function. My volume function is a polynomial, so there's no place where it's going to be undefined. So I don't need to worry about my derivative being undefined. So I just need to worry about when is my derivative equal to 0. But that can only happen if this expression is equal to 0. 0 times a quarter would be 0. So we need to set the 150 minus 3w squared equal to 0 and solve. So 150 is going to equal 3w squared. Dividing by 3 on both sides, we get 50. And then we take the square root of that 50 to get w. You get plus or minus, but we know that a negative width isn't going to be within the feasible domain. We already talked about the idea that the width can't be negative. So I only get the positive square root. And of course, 50 is just 25 times 2, not 3, 25 times 3, which is 5 times the square root of 2 equals the width. And what I want to notice is that this width is in this feasible domain. 5 times the square root of 2 is a positive number, so it's greater than 0. And the square root of 6 is bigger than the square root of 2, so 5 times the square root of 6 is bigger than 5 times the square root of 2. So 5 times the square root of 2 is an element of the feasible domain. So because I know the endpoints of the feasible domain generate volumes of 0, I know this critical number has to be the maximum volume. So we're going to get a max volume when the width is equal to 5 times the square root of 2 inches. So what I need to do is come up with the other dimensions. We need length and we need height. But length equals width from here. So length will equal width will equal 5 times the square root of 2 inches. And now we grab this guy right here and solve it for the height of the box. So height is equal to 150 minus the width squared. So the width is 5 root 2. So we're going to go 5 square root of 2 squared all over 4 times the width. So it's going to be 4 times the width. And then we just simplify. So we get 150 minus 5 squared is 25 times the square root of 2 squared is 2. All over 4 times 5 is a 20 square root of 2 in the denominator. This is 150 minus 50. So we get 100 over 20 square root of 2. Those zeros will cancel. 2 will go into 10 5 times. So we get 5 over the square root of 2 inches. And if you prefer to, you could always rationalize that denominator, but there's no requirement to do that. So I'm going to get 5 times the square root of 2 over 2 inches for the height. So the dimensions of my box that maximize volume will be 5 square root of 2 by 5 square root of 2 by 5 root 2 over 2, and those dimensions are all in inches.